Okay, today we're going to talk about trajectory optimization. Let's remember our motivation. Okay, so our goal, we've been formulating a number of times in class, the idea that we could do control design as an optimization using optimal control. Right, so the goal in optimal control is to somehow solve for every possible initial condition. I'd like to find some controller which minimizes an objective function, right? So we've been writing it often as in some additive cost, infinite horizon objective function, right? Subject to, for instance, making sure that the dynamics are satisfied and that my initial conditions are at this. This is one way to write down sort of the optimal control problem. And maybe I have some additional constraints. Like input limits or state constraints, right? But this is hard. Solving this problem is hard. In particular, it scales poorly with dimension, right? Right, if I have to check, if I have to solve for every possible x0, where x0 lives in some high dimensional space, then that becomes computationally extremely hard to do. So the idea we started talking about last time was instead to solve for a single x0. Maybe the state that I'm in right this moment, and we're going to give up on global optimality and uh, and just worry about having something that's what we call locally optimal, right? Right? The reason we have to do that is because the only way to accomplish sort of global optimality is still to look at every possible state, because there could always be some path, behind the rock over there, maybe around the tree in a way I didn't expect that could be better than the one I'm thinking about right now. So if I have to be guarantee global optimality, then there's really, again, no way to avoid examining every possible state of the system. So in order to somehow scale to to higher dimensions, I have to focus on a particular initial condition and be willing to accept only local optimality. We talked about, so the global optimality was related to the sufficient conditions for optimality, right? Which we got from the Hamilton-Jacobi-Bellman equation before. The local optimality, right? We can still give necessary conditions for optimality, right? So being locally optimal is still, of course, necessary to be global optimal, but it's just not sufficient, right? And these are the tools that we learned last time associated with Pontryagin's minimum principle, right? And just to remind you what it means to be locally optimal, right? So if I have some solution trajectory x star u star that I have as a candidate for local optimality, local optimality means if I change either x or u by some epsilon, then, well, either my cost goes up or a constraint is violated. So one of the others has to happen, and if I could say that no matter how I change x and u here, I always get worse in some way, then that's my definition that in this x and u I'm locally optimal. And again, it's a necessary condition for optimality, but not a sufficient condition. The trick is this necessary condition for optimality can be checked in high dimensions, and what's more, we can actually find locally optimal solutions in high dimensions. So we're going to get algorithms today that scale well to high-dimensional complicated robot problems. Okay. The reason it can break that cursive dimensionality is that I can write down x and u parameterized not in the dimension of the system, but parameterized only by time, right? So I can get a sort of a one-dimensional signal here, meaning, well, it depends only on time, that describes x and u. Okay, so that class of algorithms, the numerical algorithms associated with finding locally optimal trajectories, is called trajectory optimization. Let's see how it works. Okay. So the first step to make it an algorithm, right, is to come up with some sort of finite parameterization of those trajectories that we're searching for. Right, so if I write down, I'm going to try to find some u star of t, but I don't know how to search over continuous functions with the computer with finite precision, finite memory, right? So I need to somehow come up with a way to parameterize that. And there's a number of classical choices, and they're all easy, right? But so if I want to come up with some parameters that maybe I describe the value of ut at a handful of points, right? And I can call these my parameters, maybe u0, u1, u2, u3, u4, right? u5. Then these parameters here, there's a finite number of them, and they can describe the continuous function u of t if I make some decisions. So there's a couple of decisions I could make, right? I could just say that the value in between these is just whatever it was. I'm just going to hold my previous value until the next value occurs. This is that would be the piecewise constant. Or zero order hold, also known as zero order hold approach, right? Another totally reasonable approach would be to say that the function is piecewise linear between these points, right? That would be the first order hold. Or another very common approach would be to have a smooth function that goes through these points, which the standard solution would be to if you had a piecewise cubic. Which is often called the cubic spline. These are just three common approaches to interpolating that, but somehow they all share the property that I can parameterize my continuous trajectory, u of t, with a finite set of numbers, u0 through u5 in this case, and on to some amount of time. That also means I'm only parameterizing it over some finite interval, right? Let's say 0 to t, right? Okay, so once I have that, now I've got a numerical sort of problem that I can write down, right? So given this, let's give our first trajectory optimization algorithm. which is what we'll call it direct shooting. So if you give me x0 and my finite parameterized, say u0, u1 through un, then I can numerically simulate. That's everything I need to numerically simulate the dynamics. Right? And I can evaluate the cost jx0 over that finite interval, right? And that cost depends on all of these initial values. It depends on x0, but it also depends on u0 through un. Okay? But that's an easy thing to do, right? I can always, we've been numerically simulating our robots for a while now, and this is just, given this parameterization, I can certainly numerically simulate it. So what you should have in your head now is that this cost for a particular x0 depends on some finite number of decision parameters, u0 through un, right? So what I have really is a function now. If I write down u4, let's say, and I look at how j of x0 changes for different u4, and of course there's another axis. There's all of my u, so I have a different axis. But if I look just along a single axis, then j is some complicated, possibly non-smooth function of u4, right? And again, if I had to look at every possible value of j everywhere for every possible u, that's only going to work if I have a small number of u's. But what I can do by simulating, what I'm doing is I'm looking at a particular u. So right now, let's say my initial guess is this particular u. I can, by simulating, what I'm doing is I'm evaluating the function j of x0 for some particular nominal value of u. Okay? And what I'd like to do is somehow take that evaluation and move down and try to find a minima, a local minima. Right? Have an algorithm that walks down here. Now, one way to do that is to, when you evaluate u at this point, not only evaluate its value, but evaluate the local gradient at that point, right? So I'd like, if I can find the gradient of the function at that point, then I can try to walk down the gradient, move in this direction until that gradient goes to 0, right? So if you remember last time, we'll do a little extra work to compute the gradients, partial j x0 partial ui for all I, okay? But the cool thing is, the magical thing is, that computing this is surprisingly efficient using the adjoint equations that we talked about last time. Okay? So we can do a little extra work using the adjoint equations to, and if you remember how those worked, I simulate forward to get my solution x, given x0 and u. I'll simulate forward to calculate x for the entire trajectory. And I'm going to simulate backwards these adjoint equations to get partial j partial partial u. Okay. Once I have that, I have an estimate of the slope, and I'd like to somehow move down here. Now there's a couple algorithms for doing that, but almost never these days do we just do simple gradient descent. Typically we'll have some better algorithm. So let's talk for a minute about nonlinear programming, nonlinear optimization.